Welcome to our today's webinar from the EECONE project. I want to introduce you to this topic of EECONE and reducing electronic waste. My name is Moritz Schlagmann, and I'm very happy to be your host today and welcome you on behalf of the EECONE project and all of our partners, and want to thank you for your time and the effort to join our meeting today. So what are we talking about? What is the big problem we are facing and we want to challenge and improve? It's all about e-waste. So it's the global and the European e-waste. It keeps growing. So you can look at the global e-waste report every year, and you see every year that our e-waste production is increasing. And the biggest challenge is that the recycling rate and the rate how we repurpose and reuse it is not increasing in the same way. So it's almost a factor of 5 where it is increasing. So here at the EECONE project, we are working to address these issues by driving sustainable innovation in the manufacturing, in the design, in the recycling, and other 6R methods. This we are doing all together. So what is the vision of our project? Together we developed the technology for a zero waste future. This is still our vision. It's very highly aimed, but we are working on it by using and being guided by the 6R principle, which are reducing the amount of material. We are working on the reliability to prolong lifetime. We're working on repairability. We want to reuse more. We want to refurbish, and we want to recycle. And we are doing this by our 4 key objectives. It's defining green. So what are green electronic components and systems? We make them by providing new techniques. We are developing new recycling materials, but also repair methods. And now we also want to showcasing green solutions. And here we are building consciousness, and we want to share what we are doing for it and how you can also apply it on your side. So this is also an interactive session. If you have questions, please put it in the chat. And after our 3 presentations, we will go on with it. So what's the topic for today? We are having 3 presentations about our use cases. So in total, we have 10 different use cases where we want to showcase our developments. And the first session is about eco-designed remote control. So how are we building up new technologies and new products that are more sustainable, and how we can reduce the e-waste due to that. The other one is about data centers. How can we reduce the e-waste produced by data centers? How can we maybe prolong their lifetime? And the third one is about communication technology, where we can have a second life after the first life. So without further ado, let's dive into today's session. The first speaker is Edmund. He will share insights into eco-design of new electronics and setting the stage for deeper understanding for you and what we have to keep in mind. Edmund, the stage is yours.
Thank you very much for the introduction. Okay, good morning, everyone. So my name is Edmund Whitmore. I'm the environmental engineer at Whitmore Technology for the last 3 years. And today I'm going to be presenting LCA results for a normal RCE and how we've used them within EECONE to make an eco-designed version. So a brief introduction to Formod. We're a design and engineering house developing IoT and remote control products. We're primarily based in France with a factory in Tunisia where we assemble some of our IoT products. These are kind of air quality monitors and home sensors. So first, we're just going to look at an LCA from a normal remote control. We call it 3701. This work has been funded as part of the EECONE project. So we're going to look at how a remote's used over 1 year. We've used SimmerPro LCA software to make this LCA, and the EcoInvent database as our background database with primary data we've collected from our suppliers. To analyze the environmental footprint, we're using the impact method developed by the European Commission, focusing on the environmental impacts most applicable to electronics, which is acidification, climate change, particulate matter, and human toxicity. We're also looking at two socioeconomic impacts: resource use fossils, so it's just measuring how much fossil fuels we're using in the life cycle of the product, and a new method developed by Pontetel to measure the use of metals. So this is resource use dissipation. It's a slightly new method, and it's attempting to measure, once extracted from the ground, metals like iron, copper, how those dissipate into the environment. So if you have rust, for example, on an iron product made of iron, this is the rust disappears and we no longer have access to that. And we measure this through the average dispersion rate. So you'll see in this presentation ADR, and that's what that refers to. So when doing LCA, we take a cradle to grave perspective. So that means we're measuring all the environmental impacts from the extraction of the raw materials all the way through to how the product is used, all the manufacturing processes. So for remote control in the use phase, we're looking at the batteries as well. And then at the end of life, how is it disposed of? Can we refurbish? Can we recycle? Or does it end up in landfill? So this is the results for a normal remote control. We find that about 60% of the overall environmental impact of the categories we assess is from the manufacturing phase. I'll talk a bit more about why that is later. And around 40% is from the use of AAA batteries. Generally, we find similar findings for other IoT products, though the more complex products, the more integrated circuits, often you can have a higher manufacturing phase. Or if your device uses a lot of batteries, you can have a higher use phase. So a remote control has a CO2 impact of about 1.58 kilos of CO2. We take a deeper dive on the manufacturing. We find it's the PCB, the printed circuit board, that is contributing the largest percentage of the impact. This is because of the large amount of energy and chemicals needed in the manufacturing process. The housing is also quite significant. I'll talk a little bit more why later, but it's partly to do with the injection molding process. And then for the electronic components, this is mainly dominated by the Bluetooth chip. Any integrated circuit, the manufacturing process again uses a huge amount of energy and electricity. So this leads us on to our work within EECONE. We started about 2 years ago. So having identified that the electronics, the PCB, is one of the main contributors, our work within EECONE focuses on designing on an eco-design remote control using a screen printed flexible PCB. So instead of using the traditional subtractive process, where you have a big thick layer of copper, more FR4, another layer of copper, in a screen printed PCB, you just print the circuits you need using conductive inks on a very thin, flexible substrate, either paper or often PET. We're working with CEA, who are doing the printing, DTI, the Danish Technological Institute, who are developing copper-based inks, conductive inks, and Sinano are developing graphene-based inks. We're also working with Recycling and Dassault, who are helping us analyze the end of life, as well as run the LCA simulation. So we've been working with EECONE now for 2 years, and we have some good results so far. So far we're working with CEA. We've printed a fully functional PCB that you can see on the screen, and this is about 77% less mass compared to a traditional PCB. It's only about 1 millimeter thick, and because it's so thin, it's flexible. Currently, we're using commercially available silver ink, as DTI is still developing the copper ink. Silver ink is much more environmentally impacting than copper, so we're hoping by the end of the project to switch completely to the copper-based ink. This is some of the weighted RCA results. So for the printed PCB, comparing to traditional FR4-based PCB. On the right, we have PCB made in China, then traditional PCB made in France, and then we're comparing, since we're switching manufacturing to France, we can have a like-to-like comparison to the flexible printed PCB made with silver ink, which we've achieved now, and the copper ink that we're working towards by the end of this year. The copper-based PCB shows about a 68% reduction, and the silver slightly less. The silver is the main delineator between the copper-based PCB and the silver ink. We really want to try to avoid using silver where possible. So we can change the PCB. We can also change the housing. It's a bit more straightforward. We can use recycled material. We reduce the impact by about 50% by using recycled plastic. But we can also change the way we do injection molding. This is one of the more surprising results, was actually the injection molding process itself for small components uses a huge amount of energy, especially if it's done with hydraulic injection machines that are traditionally used in China. So by switching to electronic injection, you can reduce the environmental impact overall by about 45%. Finally, we look at the use phase. So at the top here, we have the normal remote with a standard, quite efficient Bluetooth chip. If we use the state-of-the-art Bluetooth chip, we call that green mode V2, we can reduce the number of batteries from 4 to around 3 for the whole life cycle. But what we really want to move to reduce e-waste is a batteryless remote. So we've developed, we've been working with a partner who have developed a bio-based photovoltaic cell. So very thin, kind of almost a membrane that you can put underneath the keys of the remote and replace the need for traditional batteries with the OPV cell and a hybrid supercapacitor. And as you can see, this dramatically reduces all the environmental impacts. So let's bring it all together. So we have, let's compare 3 different versions. So we have a traditional remote, 3701, which is what I showed you at the beginning. We have where we are today, which is 370E. So this is a remote with the PCB, flexible printed PCB with silver ink and mechanically recycled plastic, as well as an energy efficient Bluetooth chip. And then where we want to be by the end of the year, by the end of the EECONE project, is with a flexible PCB with copper ink, same plastics, and an OPV cell. So the results are very promising. Just going from 3701 to 3E, where we are now, we have about a 33% reduction in the overall environmental score, and we don't burden shift by contributing to a different impact category more. There's an overall reduction in all of the environmental impact categories assessed. This is even further for the Mirage Solar. The results are still provisional. This is based on laboratory scale data. So we expect once we industrialize the flex PCB manufacturing processes to the same scale as we produce millions of remotes, we'd expect a further reduction. So we achieve a 70% reduction with the Mirage Solar. So we're almost saving a full kilo of CO2. And given that there's a production volume of 300 million remotes a year globally, it's a kilo for one remote isn't a lot, but on a global scale, it's a lot of CO2 saved, as well as we achieved the 52% reduction. So a bit more work to do, but we're nearly there. So I hope that all made sense, and thank you for listening.
Thank you, Edmund. I think this is a great showcase to see what everything comes together from PCB replacement, printed electronics, housing, recycled materials, and you make it visible by having the LCA. Just having an LCA for the purpose of having it doesn't make so much sense, but you make sense out of it and you see the hotspot. So from our audience, if you have any questions to Edmund, please put it in the Q&A session on the bottom right side of the window. There's this Q&A, and you can type in your questions, and we will answer them at the end. We are happy to hear from you and get your insights as well. The next use case we want to show is presented by John. It's about improving data center sustainability via the reuse of electronic systems. John, the stage is yours.
Thank you very much, Moritz. Yeah, so my presentation should come up very soon. Hopefully you can hear me all clearly. Yes, yeah, thanks. Yeah. So this is use case 7 in the ECONE project, which is looking at improving data center sustainability via the reuse of electronic systems. So these systems are made up of lots of components. Myself, I am a scientific lead in data center research at RISE, Research Institutes of Sweden. And I also have a number of other titles honorary titles associated with universities. Yeah. So basically, RISE. Just a little bit about RISE before we get started. Is one of Europe's largest research institutes. It's actually a collection of research institutes. It's state-owned. Quite a few, many employees. We pride ourselves on our diversity as well, and also our interaction with industry and academia, with a number of test beds and demonstration environments across, and it's located in multiple locations in Sweden. The facility that I work out of is actually the ICE data center test and demo facility, which is in the north of Sweden. This is very, very close to the Arctic Circle. And data centers produce a lot of heat, and it's easy to get rid of heat in cold climates. We've got a number of test beds there where we're testing all different kinds of things around the data center infrastructure. It's more about operations and energy efficiency, as well as now the topic of sustainability is very strong within the data center community. Understanding the impact of the electronics that goes into data centers is very important and part of this project as well. So we run an ICE, what they call the ICE Connect portal, and we run some live data centers. So they actually are production data centers, so we can do a lot of testing in a live situation. So basically, maybe the first question we should ask is, what does a data center look like? And actually, what I decided to do is take actually some photographs of a data center which is located very close to us. So this is the Facebook data center. It was one of the largest hyperscale data centers in Europe, which is in Luleå. To the top left there, you can see the actual building itself. To the right, you can see actually 3 buildings. I don't know whether you can see my mouse here, but there's 3 buildings, and this is pulling a considerable amount of electricity off the grid. But the main thing is, inside the data center, we have racks of servers, and the servers are all electronic systems. So data centers are there to store, process, and transmit digital information, and we use them every day in our daily lives. And you've probably heard from some media articles or in the news that data centers are popping up all over the globe, and we're building these things, these systems at a tremendous pace now with the advent of artificial intelligence and the use of artificial intelligence in so many different applications. So looking at, first of all, one of the indicators is the actual energy consumption. And I think this is an interesting graph that was produced by the International Energy Agency, Electricity 2024, and it was an analysis and forecast to 2026. And one of the interesting things is post-COVID, there was the decline in electricity consumption within Europe. But recently, what we've seen in 2024 is an uptake of an increase in demand for electricity. And there are essentially three main components to that, as the electrification of mobility, the electrification of heat in terms of electric vehicles and heat pumps, but also data centers. So there's an additional 29 terawatt hours that's estimated to be added to the electrical demand within Europe between 2024 and 2026. And this is all to do with data center processing, which predominantly, some of this is AI activity, but also we're digitalizing everything. The whole European digitalization program is where digital activity comes into everything we do on a daily basis. But at the same time, there is a massive growth in data that we store, which is also part of what I wanted to talk about in this use case. So this is from the World Economic Forum in terms of looking forward, in terms of the data volumes in zettabytes or zettabytes here, which is quite considerable growth. That is an exponential growth there in data storage that's required for the future. And of course, coupled with all this is actually, depending on the electricity source where you actually place your data center depends on the carbon intensity of the data center. And so there are estimates as well about the percentage of electricity consumption by 2030. And there are different scenarios, and these scenarios depend on probably financial situations, geopolitical situations, and also the demand growth, particularly in the AI sector at the moment. So in terms of the use case that we've got here, there are two aspects to use case 7. There is a theoretical research, which is led by my colleague Parvati Tampi. And there's also an experimental research part of that, which is looking at repurposing electronic servers. We call them servers. They're electronic systems within data centers. And that's led by my colleague Tina Stark at RISE as well. And that involves some of the partners in the EECONE project. Both do, should I say. So there is a connection also to, and I think this diagram is also used in the next use case as well, but you can see data centers are actually on the dark side of the moon, if you like. They don't actually really exist on the dark side of the moon, but it's something that you don't see. The devices you have in your hand, or your laptops, your iPads, your smartphones, they are talking to data centers verbosely all the time. They're connected to data centers. And they're connected via an infrastructure, a network. But the data center you don't see, and the data center is obviously doing a lot of the hard work. They're the engines that drive the digital economy. And so there's another picture there of inside a data center where you can see racks of IT equipment. And this is where we want to focus our attentions on the electronic waste from the actual servers that sit in data centers. So one of the things that we did very early on in EECONE was to say, well, whenever you look at servers obviously are doing a workload, and that workload is growing, but we have considered an approach that was in a very interesting paper written in 2018, which was a comprehensive reasoning framework for hardware refresh in data centers. And that was looking at servers between 2007 and 2016. And it essentially was looking at how the server has improved in terms of its energy demand for the actual amount of work it can do. So the work it does is digital, and the demand is obviously on the electricity that it needs to use. And this can be captured in what's called the Standard Performance Evaluation Corporation's analysis spec data. And that's going forward, we can look on the right here, we can look at a scenario where you've got existing hardware. You bring the hardware into the data center, it brings in carbon. There's a huge increase in carbon as you build out your data center with all your servers. And then when the servers are in use, they are constantly consuming electricity, which has a carbon intensity. So that carbon is accumulating. But at some point, you will make a decision whether you want to refresh the actual hardware, and then there's an increase in carbon. But because the servers that you've replaced are now more energy efficient, doing the same amount of workload uses the gradient of the curve has changed because your consumption of electricity for the same amount of workload has decreased, and so there's a break-even point. Which could, based on carbon, could be the point at which you should refresh the hardware. Now, the only information that we can get for servers these days is very carbon focused, carbon myopic, is actually what's called, these product carbon footprints that are provided by servers. This is actually the server manufacturer Dell with one of their servers. And one of the interesting things is there's some analysis here of the running this server on the average of the EU grid in its production phase. It's 15% carbon is embedded in the item in the server, and 84% is in the use case in the use phase. Whereas in Sweden, for example, I mean, this is actually from our partners Atea, which are a Swedish company, and they sell data center servers to the market. The production phase is much higher, 63%, because compared to the use phase, because the carbon intensity of the electricity grid within Sweden is much lower than the average for Europe. And so you see different scenarios here, depending where you put your data center. And we have done this analysis in a scientific approach here, where we've used the same kind of approach as I mentioned in the Bash-Roos paper for 2017 to 2016. We've been looking at servers from 2017 to 2024. And this is the IT workload remains constant in this analysis, and that is probably an assumption that is not correct, because workloads are increasing as more and more demand comes on. But this is work presented by Parvati at the DATE conference in 2024. And to the left here, you're seeing the use phase drop because we are decarbonizing our grid. So this is actually, again, focusing on Sweden or the Nordics. And there are three different scenarios here. There's a scenario where you don't refresh. So it's the in-use phase carbon when you don't refresh, which is the green curve, or I think it's a blue or green. And then there's if you refresh in 3 years. So that's why we take starting from 2017, refresh at 2020. And then there is the refresh at 5 years, which is 2023. And the interesting thing to the right here is the fact that we don't see actually a crossover, but you do see the accumulated carbon in this kind of scenario is if you don't do the refresh and allow your IT to run for a considerable amount of time. This is actually 10 years from 2017 to 2027. Ultimately, when you get to 2027, the accumulated carbon is less than if you did the refresh in 3 years, or the refresh in 5 years. So, depending on where you run the data center would dictate when would be a good time to refresh based on carbon. But of course, so like in the previous presentation, there is an in-use phase, which is changing for data centers because the grids are becoming decarbonized. So at the moment we've got we're focusing on the in-use phase being much larger than the embedded. But as we decarbonize the grid, depending where the servers are usually manufactured outside Europe, the embedded carbon is becoming a much larger percentage of the whole carbon assessment for data centers. So these are important things that we're trying to bring in. But it's not just about carbon. It is about other aspects, because we're using resources. We're using a lot of critical raw materials. So in terms of the life cycle assessment, which I don't have any results yet, we're still building this on the base of the bill of materials, which is quite challenging to get hold of. So this is actually all the material components that make up a server. Here's a server on the left here with the lid taken off. You can see a lot of memory and a lot of components in here, a lot of different materials. And with one of our partners on the right here, we're looking at the bill of materials for the what we're calling the power supply units. The power supply units are modular, and usually there are 2 power supply units in servers because they are connected to 2 electrical distributions for robustness. And we're getting a much more detailed bill of materials for the actual power supply. And IMP Grenoble are actually looking at a different design of power supply that makes them more efficient and perhaps more reliable. And we will also do that as part of the see the impact of that approach on the life cycle assessment of the server. The other thing that we're doing is we're looking at second life of servers. So what you can see here is actually to the left here, you're seeing a video footage of some old 2U servers. When I say 2U servers, that's the actual height of the servers that take up 2 units. And we're repurposing these servers that were compute servers to storage servers. So now we are populating them with a lot of disks. So if you look to the left here, you can see a lot of the disk bays are now populated, and we're distributing storage over this. And this is to look at to see whether how much the robustness would be of actually converting a compute server into a storage node. But if you distribute the storage over a large number of servers and a large number of disks, even though the servers may be, because they're quite old, may be liable to fail, in this scenario, we want to look at, in an experimental way, if we lose a server, how easy is it to rebuild the storage system? If we lose disks, how easy is it to continue operation? And the way that we're doing this is we're using the Swiss Vault, which is another partner within the use case 7 and a partner of EECONE, to use their advanced erasure coding technology, which is this is a software environment, and to build out a cluster, a storage cluster on repurposed servers that were once compute servers, but now are storage node servers, and looking at taking out one of the CPUs so that they use less electricity, because they don't need to do a lot of data processing. They obviously need the CPU to interact with the user, to obviously recover to serve the data, but at the same time, we're running a lot more hard disks within the. But we're going to monitor the energy consumption of all the components and put it through the paces to try and understand in a real life scenario how this would look like from an environmental footprint of repurposing or reusing the server in this way to increase its life through a second life. And the second life of the servers, a storage node, is going to involve us setting up a before scenario, which allows us to run with what's an industry standard, which is called Ceph, which is a particular way of distributing storage within the server. Establish a baseline based on the terabyte, the carbon cost per terabyte, and determine the robustness of that through redundancy and replication. And we'll measure the life cycle carbon within that baseline scenario. And then we will do the same thing again, but this time using the Vault file system from Swiss Vault, where we will do the same kind of calculations to test against the baseline to see what kind of environmental savings we can make by putting these servers into a second life scenario. So some of the infrastructure, some of the tests that we will do will test the compression algorithms that the Vault file system uses, and we will obviously stress the system by failing a server over and failing disks over to see how that creates a robust storage solution. The performance of the storage solution is also very interesting, and so that could be a question that somebody may have. You know, does this produce a storage system that gives good performance? And with that at the moment, that's all I have to say at the moment about use case 7. And I thank you for your attention. And I guess that we will have questions towards the end of the session here today.
Exactly. Yeah. Thank you very much, John. Great overview and a very pressing topic, I would say, as it's increasing demand of data centers, and we want to do it in a sustainable way. Otherwise, we are not going anywhere. So again, if you have questions, put it in the Q&A session. I've seen there are already some for Edmund, so take also some for John. And with that, I would hand over to David. So coming from the dark side of the communication systems, which are not very visible, coming now to the brighter side, maybe.
Thank you. Brighter, indeed, I suppose that they are more visible because what we will focus on, or what we are focusing on in use case 8 is the networking equipment that are more visible indeed for the consumers or the users of ICT in general. And the target that we have there is to reduce their electronic waste of the networking equipment with two specific means, and one of them being repurposing obsolete smartphones into modems or networking equipment that are then circular because they use used or they reuse electronic parts in a second life fashion. So if I use the same illustration as John earlier, we've seen that.
I cannot see your slides. Maybe you need to press again a button.
Oh, yes, I'm sorry. I have to confirm this.
Again,
Yes, now you see it.
perfect. Thank you.
All right. So what I was saying is that if, as John focused on data centers on the dark side there, here we will focus, or we are focused on what we call the customer premise equipment, that are networking equipment like modems, routers, gateways that we have in our home that allows us to connect through Wi-Fi or to Ethernet to the fixed access network, so DSL network or fiber network. And they are called customer premise equipment because these are owned by the internet service provider that you select for having fixed internet at home. There is a variety of modems and CPE equipments that are available, and we focus specifically on the one for DSL and optical fiber access to the home. And this is done in collaboration with several partners. You see Louvain that I am from is leading that use case. And we have Thales focused on the security aspect of these developments, Fraunhofer for packaging and mechanical structure and operation to these CPEs, Feria for the robustness of the CPE, CEA for future generation or next generation with eco-design in mind, IMEC for modeling of the carbon footprints and the different environmental impacts of these devices. And then we have two partners that are not within EECONE, but that are our local national partners for this use case. There is Proximus, who is the internet service provider in Belgium, so who is one of the providers that supplies the users with ECP equipment, and Citronics, which is an SME in repurposing of smartphones. So there is the motivation that we have there is that CPE equipments that we have in our home tend to have a replacement that is not as frequent as other user devices like smartphones, for example, but they still have some replacements for two reasons. Either because of functional failure, and this is quite rare because those devices, they don't get like plugged and unplugged very often, so their interfaces stay strong. They don't have a screen that can be broken. They don't have a battery that can die out. So they are not really replaced on a frequent basis because of functional failure. It happens, but it's rare. However, there is a performance obsolescence coming from the evolution of the communication standard. For example, moving from Wi-Fi 5 to Wi-Fi 6, from DSL to fiber to the home, optical networks. So there is an evolution of the standards that leads to a replacement and end of life of those products. So to reduce electronic waste coming from these transitions, we have two levers that we are trying to activate in use case 8. The first one is having a modular design as an eco-design way to be able to replace only part of the system when we want to update it instead of replacing the whole electronic system. And the one that I'm going to discuss now in the rest of this webinar is the second option, which is repurposing obsolete electronic parts into modem CPE. So there is a legal framework around this, which is called the Router Freedom Framework, which is an initiative which is spreading in Europe. You see here the countries that have, or the states that have validated this router freedom concept at the legal level in Europe. and Belgium is one of them. And so the idea there is to let the users of fixed internet access be able to select their modem irrespective of the internet service provider that is actually providing them with the internet access. In Belgium, it was adopted in 2023, and it's still progressing in Europe. So the idea would be that it would be possible for a customer or user of internet access to actually select his or her modem based on environmental concerns by having a circular modem coming from obsolete parts that are reused, instead of just selecting the one that is provided by the internet service provider. Or the internet service provider can have an eco-friendly options for their modem that would be using repurposed electronic parts for this objective. So the concept and the target demonstrators we have in EECONE project is first to generate an equivalent of a 4 to 5G or 4-5G fixed wireless access modem. So it's a modem that allows you to have access to your different Wi-Fi or wireless LAN clients like a desktop, laptop, a printer, or connected objects in your home with a fixed access, but with wireless communication to the mobile access network with 4G and 5G base station. And the idea is to reuse an obsolete smartphones that would make the job of this fixed wireless access as a type of hotspot for that purpose. It will be a second life phone, and it will be a phone that is obsolete, either because its memory is not able to sustain the new versions of the applications that have become more heavy over time, or because its screen is broken, but actually we don't need its screen, so we can reuse it that way too. And obviously we don't need its mobile or its battery either, because this can be plugged in at all time. And the second target demonstrator is to replace a DSL or fiber to the home, FTTH, or optical network modem and router that are usually called home gateways by internet service providers, by also reusing or repurposing an obsolete smartphones. But there, because the obsolete smartphone doesn't have the physical interface to the fixed access network, be it DSL or fiber, then we will need to add a USB interface to this specific physical access network. Now, there is a state of the art in this field. So Citronix, the partner that we have, which is an SME in that field, is already providing a circular generic computer that is sourced from repurposing obsolete Fairphone 2 models that they dismantle, they extract the motherboard, and they use this motherboard placed on a custom PCB to provide a wide variety of accesses like Ethernet and USB accesses to this phone, plus supply of this electronic board to be able to reuse the memories and the computing elements for the application processor into it. This year at the Mobile World Congress, Dutch Telecom, which is an internet service provider in Germany, has also demonstrated a first modem for DSL access based on the Fairphone 2 model, where they extracted the same motherboard as from Citronix, and they use it to make CPE, which is a router for DSL access. So it's something that is progressing, and it's at least emerging, I would say, in Europe, to repurpose smartphones into different type of appliances or electronic equipment. Now, the objective in EECONE is to start from this existing state of the art, which is based on the Fairphone 2 model, and to go a step beyond by looking at what could next generation of smartphones, the smartphones that are currently in use and that will become obsolete in a few years, typically at the end of the project, 27, 28, and what they could bring in terms of additional performance and functionalities, and what are the pitfalls for repurposing them in an efficient way. So the differences with the current state of the art is that the SIM card that allows you to connect to the internet service provider network can be removable, but can also be using an electronic SIM based on the secure elements inside that phone, and we need to be able to take the control over that element. The cellular access is improved from 4G LTE to 5G and R type of communication. The Wi-Fi capabilities has been expanded from Wi-Fi 5 to Wi-Fi 6 or 6E. The USB standard has moved from USB 2 to USB 3.1, and therefore we hope that the modem performance will be much better with this new generation of smartphones to repurpose. And here we have specifically selected Google Pixel 6 because of wide stock of phones and because of an opening perspective that Google has on its reprogrammability of those devices. Now, the current status that we have in EECONE is that we have a repurposed smartphone that is a Google Pixel 6 that we complement with an Ethernet to USB dongle, which is an external devices that is able to connect to DSL or to GPON for optical network interface, and that provides Ethernet over USB communication to the phone, plus the 5-volt USB power to the phone. And inside the phone, we find elements that are useful for the modem functionality. Of course, the application processor is very central because it performs all the central function of the CP, of the modem or the router. We need to have the cellular interface SoC to be able to have the access to 5G and 4G communications for the fixed wireless access router. We need the Wi-Fi or WLAN interface system on chip to have access with it. That requires to take control over the PCIe port inside the application processor. The application processor works with the SSD disk and with the DDR memory, and the cellular interface also relies on the SIM and eSIM for the authentication with the internet service provider. There are several devices or several peripherals that we don't need. The screen, the other peripherals, this should be disabled for power saving. And the battery is left into the smartphones as a way to buffer potential interruption in the 5V power supply. But essentially, most of the power is really coming from the 5V power supply at all time. From the software stack, what is very important is that we don't want those repurposed smartphones to be dependent on Android releases, because when the phones becomes obsolete, there are no further security updates on Android kernel, and we would like to be using the mainline of Linux kernel in order to be sustainable from the security standpoint for a number of years after the phones becomes no longer supported by Android. So to do so, we rely on the mainline of the Linux kernel, and below it, we need some drivers, including drivers for the wireless LAN interface, drivers for the PCIe, drivers for the USB interface as well. And for these ones, we actually recover or extract them from Android kernels as stable drivers that do not suffer from severe security pitfalls over time evolutions. And then on top of it, we need an access point type of management to perform the router functionality over wireless LAN. And for this, we used an open source release or open source piece of software, which is Host APD. Now, with this, what we have done so far is using this phone as repurposed element for Ethernet router, and we comparing with the Fairphone 2 with 1, 2, or 3 client devices that are connected to the Fairphone 2 as access point or to Google Pixel 6 as access points. What we see is that the throughput that was limited to 100 megabits per second is widely improved with the Google Pixel 6 thanks to a wider bandwidth for the Wi-Fi communication and to the higher modulation index. So in the end, as a conclusion, we really believe that the use of current generation smartphones that will become obsolete in a few years from now will bring really enough Wi-Fi capacity to replace home gateways in our domestic appliances for networking equipments, and we'll be able to source really circular modems based on these obsolete smartphones in a few years from now, having then a way to limit the production of new networking equipments for this specific target. Thank you for your attention.
Thank you very much. Also a very nice use case to show yeah, what is possible. Where can we save e-waste? What can we do about it with innovative ideas? And obviously, it is not easy to do so. You showed the challenges. You need interconnections. You need additional software. You have to take care of security. But you are addressing these issues, and I think that's a great way to go. So if you have questions, we have still now 10 minutes left. You can put them in the chat. I have seen that Edmund is already answering quite some of them, but nevertheless, Edmund, do you want to start off and maybe comment on what I personally think is very interesting, that you put photovoltaic cells under the remote control keys.
Yeah.
So this is kind of a new technology we're also developing in the project.
So yeah, it's not the technology isn't developed directly within the project, but we're assessing it through some of the LCA partners in the project. So it's a very thin OPV cell. It's less than 1 mil thick, and it's flexible, which lets you actually press through as if it were a key. So you can have your metal dome, which we use as in remote controls to have that kind of pressing click function. You can have this over that and then numbered on top, and you can press through. We're still in the integration phase, so we have some functional demos, but we don't know the longevity, how long these cells last. So we're still doing testing to confirm that, you know, within 5 years, 8 years, you still have a functional remote control.
Yeah, very interesting as well, the reliability coming in. And I've seen you've received a lot of questions regarding, let's say, technical discussions on how you assess the LCA, but you've already answered them.
But maybe I can mention a bit. So I've shown some weighted results here just for the ease of science communication. But I should note that weighting is, you know, we use the weighting method provided by the EU, and it's done through the weighting. They've calculated this through like a survey of LCA experts and to determine which impact categories are more important than the other, but it's still relatively arbitrary. So behind the scenes, we are checking across all the impact categories to make sure we're not burden offsetting, impacting land use more than, say, climate change. But generally, within electronics, especially with flex PCB, because you are just using less energy and less chemicals, you tend to see across all the impact categories a pretty consistent decrease. It's more, we've only had problems with burden shifting when we look at things like bio-based plastics, where you often have like land use change impacts. But there's more behind the scenes, and then when it comes to science communication, we show the weighted results because it's a bit more accessible rather than showing normalized results. It can be a bit hard to get through.
Absolutely. So I guess there will be also some scientific publications. There are many scientific publications around this topic. So you see that there is a lot of need to be very clear, and this is one of our goals in the project, to define ACS and make it clearer. Okay. Yeah, thank you very much. Maybe a question to you, John. Could you estimate the amount of the data service that would actually need some upgrade? Would it be possible to have this part removable from the total hardware in order to reduce the replacement environmental impacts?
So this is a very difficult question to answer because data centers, depending on the applications that they're serving, will dictate their refresh cycle. So a lot of data centers will operate with a refresh probably at the end of the warranty if they don't want to increase the warranty, and sometimes these warranties are 3 years or 4 years. But there are data centers that actually refresh hardware in less than 2 years, and that's because they want the next generation technology. And perhaps the servers are not so easily upgradable themselves, so it's easier to remove the servers and to replace them with the newer servers. And Of course, a lot of the interesting thing about this is one of the things that is not so changing so fast is actually the RAM in servers. The RAM in servers seems to have a much longer lifetime, so that can be recovered and sold on a secondary market. Because it's compatible with a lot of different, it's even compatible with desktop devices and things like that. So it really does depend on the application. And I don't have any percentages. The Uptime Institute, which is an organization that tracks the market for data centers, has done an analysis on when data centers do their refresh, what percentage refresh at 1 year, 2 year, 3 year. And there are data centers that are operating servers up to 6 years. They're still in operation after 6 years. But it's all about the technology changes and getting access, because it goes back to that issue that if you can do 4 times more work for half the electricity consumption, why don't you refresh with your next generation hardware? Yeah? So I can't really answer the question with the actual percentages. Yeah.
You need this holistic look, not just energy consumption, but holistically material used, everything that you are addressing as well.
That's absolutely the case.
Driven refresh.
Yeah. Yeah.
Cool. David, maybe a question for you. If you have the second life, do you expect the repurposed building blocks will reach their functional end of life during the second life cycle, so as a router, or do you anticipate a potential further cascade of repurposing?
Yes, I saw the question. I think Caroline raised it. Thank you, Caroline, for this interesting question. So if you look at the reason why smartphones are actually replaced today, either it's because the screen is broken, the battery is dead, or the USB connector has an issue, or there is functional obsolescence because of the memory that is full, or there is no update for the software. We don't expect this to happen here. There will be no mechanical usage or mechanical operations with the smartphones in their life as a modem. So I don't expect them to reach their end of life for that reason. Also for the updates of the applications, because we will be relying on the mainline Linux, it will be supported over time. So I don't expect obsolescence from the functionality security aspects there. Of course, there might be performance obsolescence, assuming that people would like to move to Wi-Fi 7 maybe in a few years for the access at their home, so that can happen. And in this case, that could be, we could envision a third life with those smartphones. The only reliability issue that is there is from the power consumption standpoint and aging of the devices, because the usage of a CPE or for modem is very different from smartphones, because smartphones stay most of its time in sleep mode, which is not the case for CPE by default. And so there is important work to do at the power management level to make sure the phone is not consuming 5 watts at all time, just for the carbon emissions of the usage, but also really for the reliability of the phone itself, because it hasn't been designed for that. It's much more integrated than a CPE, than a modem, and so it has less heat dissipation capacity, and we need to make sure power management is done in a proper way with this respect. So I suspect that the end of life will be quite far away, but still maybe a third life would be an option.
So they have an easier second life, not so much mechanical stress, and the typical obsolescence is not as a direct burden to them. Cool. And with that, we're already at the end of our webinar. I want to thank you, the speakers and the organizers, for making it possible, but also for you, for the audience, to join our talk. And I hope to see you again in our next webinar. Thank you.
Thanks, everyone. Bye-bye.
Thank you. Bye-bye.